Okay, we're picking up where we left off in section 2 of chapter 2. In this video, we're going to go through the second half of this section, section 2.2. So in the previous video, in the first half of this section, we went into detail on the general meaning of limits and how limits are evaluated. We haven't made any official statements yet on the definition of the limit. We're going to make official statements about limits in section 2.4, but we're starting to get an intuitive feel for what exactly limits are. Okay, and so now in this video, we're going to talk about two specific categories of limits: one-sided limits and infinite limits. Okay, so let's start with one-sided limits. So as we saw in the previous video, for a general limit to exist, you need to be approaching the same output value as the input value A. So in general, we say that a general limit is you've got the limit as x approaches A of f of x is equal to L. Okay, so for a general limit to exist, meaning that there is some specific unique value L for the limit, then what we saw in the previous video is that in general, you need to be approaching the same output value L as the input value A is approached from both sides. So approaching the input value A coming from above A and coming from below A. Okay, but we can also think about specifying a limit that applies only as the input is approached from one side. Okay, and this is what's called a one-sided limit. So, okay, the Heaviside function h is defined by, so the Heaviside function h of t, you input a value t into this function, and what's the output? The output is 0 if t is less than 0 and 1 if t is greater than or equal to 0. Okay, and so we can graph this function as shown here. If the input t is anything that's less than 0, but not equal to 0, so there's an open circle here, then the function is equal to 0. If the input is t is greater than or equal to 0, then the output is equal to 1. All right? So now it says, as t approaches 0 from the left. So we're wanting to think about limits as t approaches 0 of this Heaviside function. Or equal to what? So as t approaches 0 from the left, h of t approaches 0. As t approaches 0 from the right, h of t approaches 1. So what do they mean by that? Well, okay, if we think about from the previous video, the first part of this section, we can deduce that what they're saying is, so if we go back to our most intuitive understanding of a limit from the perspective of like an infinitely powerful calculator, okay, if we're approaching 0 for the Heaviside function coming from the left, from below 0, then what we're doing is we're plugging in to this function values that are closer and closer and closer and closer to 0 coming from below 0. And with this enormous calculator, we can hypothetically do this with thousands of digits. So that would be like plugging in h of minus 0.01, minus 0.001, minus 1,000 zeros 1. But never 0 itself, just a sliver below 0, and then evaluating the result of the function. And so if we had a table and we were doing that with this huge calculator, what would we be seeing that the output's doing? Again, we do not care what's happening at 0 itself, not at all. All we're thinking about is this. We could actually use one of our graphing calculators, or we could really think about the precise definition of the limit. We want to think about this an infinitely powerful calculator. But if we were plugging in these tiny values just below 0, again, minus 0.01, minus 0.001, minus 0.00 1,000 zeros 1, minus 0.000 a million zeros 1, minus 0.000 a trillion zeros 1. And we could, the function exists, right? And the Heaviside function exists, and we were looking at the outputs. Well, they would all be 0. As long as we never got to 0 itself, we were always just a sliver below 0. Every output would be 0, 0, 0, 0, 0, 0, right? That's the definition of the function. And so that's what they're saying. Coming from the left, h of t is approaching 0. And then similarly, if we think about approaching 0 from the right, so you're plugging in positive 0.01, positive 0.001, positive 0.000 1,000 zeros 1, positive 0.000 a trillion zeros 1, every one of those outputs would be 1 over and over and over again, as long as we never, well, in this case, we could plug in exactly 0 and we would get 1, but that's irrelevant. We don't care about what's happening when evaluating limits. We don't care about what's happening at the limit value itself. So we would be seeing over and over and over again the value 1, no matter how close we got to 0 from above. So the limit as t approaches 0 of h of t coming from above 0 is 1. Okay, but what you can notice there is that there's no single number that h of t approaches as t approaches 0. And so therefore we state that the limit as t approaches 0 of the function in general doesn't exist. We would state that this limit doesn't exist. Okay, so you might be confused and wondering, well, so why are we saying the limit doesn't exist? I mean, we just specified 2 limit values associated with t approaching 0 of this function, right? So, but it doesn't exist? Well, no, because the limit doesn't exist as t approaches just in general 0 in this case, because we need to have a specific, unique 1 value being either sandwiched or that same value approached from both sides, right? Like, think about evaluating a limit from the perspective of actually trying to figure out some information, which is really what we're going to be doing in practice. So like we did with the slope of the tangent line, those limits in the previous section. Well, we need those limits to be approaching a single distinct finite value, right? With that single unique value representing the slope of the tangent line for that specific problem. Otherwise, it wouldn't make sense. We couldn't be getting more than 1 value for the slope of the tangent line. Okay, and so that's why those limits existed. We were sandwiching, for that problem we worked, we were sandwiching the value, I think it was 2. And that's why we stated that the limit existed, right? So like here, when you come from either side of the input value, there's 2 separate limits. Well, what are we going to do with that? The limit doesn't exist. There's not, if we're thinking about some actual physical situation that we're analyzing, that we're applying math to, we need a unique value for the limit to make it useful, to make it make sense. Here, you have 2 separate values coming from both sides, so we say the limit doesn't exist. Okay, however, though, it is true that as this function is approaching 0, it's not like limiting values don't exist in some sense, right? Yes, we did just state how we could analyze this from the perspective of approaching 0 from the right, the limit as the function does approach 0 from the right. We could state that the function, the output function value approaches 1. And coming from the left, the output function value does approach 0. And this could potentially be useful information. Like, for example, if you think about with some system, we usually don't care about times that are less than 0, right? Like time starts at 0. So maybe the only information we need here is what the function approaches, the limit of what the function approaches as t approaches 0 only from the right. We aren't concerned with what the function is doing approaching 0 from the left. Okay, and so that's the whole purpose of what we call one-sided limits. So we could make a statement that if we wanted to state that, okay, the limit as t approaches 0, and instead of saying in general, so like just from the left and the right, which this would be implying, we could specify that, okay, only considering t approaching 0 from the positive direction, which would mean from the right. So t is approaching 0 from above 0, not the positive direction, because you could maybe have t approaching -5, and so like, I guess you could call this the positive direction, but from above the value of h of t. Okay, well, in this case now, since we're only concerned with approaching the input value from one direction, well, we saw this limit, we would say, does exist, and it's equal to 1. And then similarly, if you wanted to specify a one-sided limit coming from the other direction, you would put that t is approaching 0 from below 0, the negative direction, and we saw that would be equal to 0. Okay, and so these are what are called one-sided limits. You identify a limit as being one-sided by going to the input value and looking for is a plus or a minus indicated. But if no plus or minus is indicated, then you're not dealing with a one-sided limit. Then this is making a statement that the limit as t approaches 0 in general from both sides. Okay, so now if we think about similar to what we did with the intuitive definition of limits in general in the previous video, we can think about an intuitive definition of a one-sided limit. So we write that the limit as x approaches a, and they're going with we call this a left-hand limit first because we're approaching a from the left, of f of x is equal to some unique value L. So this limit exists if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a with x less than a. So it's the whole idea of it, the infinitely strong calculator thought exercise, just like we did with in the previous video with general limits. For a left-handed limit, if we can plug in values of x into the function that they're never at a. I mean, we could plug in the x is equal to a just for analysis if we want, but for officially evaluating the limit, what's happening at x is equal to a doesn't matter. Okay, but if we plug in values into this infinitely strong calculator of x that are just below a, okay, and with this infinitely strong calculator, we could get as close to a from below a as we want. And we would continue to get output values no matter how close to a we got. And we would see clearly that the closer and closer and closer and closer and closer we get to a from below, the function is getting, at the same time, getting closer and closer and closer and closer and closer to some value L. Then we say that that value L is the one-sided limit, the left-hand limit. And it's a similar idea with a right-hand limit. Okay, and then it's similar to what we talked about in the previous video for general limits in regards to, well, how close is close, right? For this limit to exist, then how close do we need to be to a? Well, technically, it doesn't matter how close as long as at some point, so we could be making this table of the input x values. Okay, here's x, here's f of x. Okay, now we're thinking about the limit as x approaches a from the left. Let's say we're thinking about as x approaches 2 from the left. Well, we could start plugging in values of x like minus 1, 1.2, 1.5, 1.75, and maybe the function doesn't even exist at those values. Maybe the function doesn't even exist at 1.9, 1.99, 1.999. But as long as at some point, if you got to x is equal to 1.999, 1,000 nines, then all of a sudden the function started to exist, and you start to get outputs. And then you kept going, 1.999 a million nines, 1.999 a trillion nines, 1.999 a quintillion nines. And you were, at those points, you were getting output function values. Your calculator could determine those values. And you were clearly seeing, as x got closer and closer to 2 from just below, all we care about is below with this one-sided limit, this left-handed limit, you were seeing that the outputs were getting closer and closer and closer and closer to some finite unique value, L. Then that's good enough. You're close enough. You're sufficiently close to A with x less than A, and the limit exists, and that value L is the limit. Okay, and again, the right-handed limit is the exact same idea, except x is approaching A from up above A. Okay, and so what we can think about is that based on everything we just talked about, so the limit as x approaches A in general, so not a one-sided limit, of f of x is equal to L if and only if the left-hand limit as x approaches A of f of x is equal to L, and also the right-hand limit as x approaches A of f of x is equal to L, right? That's the only way the general limit as x approaches A of a function exists. So this is making the statement of how for a general limit to exist, as we talked about, you need to be coming from both sides of the input that's specified, the A value, you need to be sandwiching an output, or it doesn't have to be sandwiching. It could be sandwiching, or just you're approaching the same value from both sides. That has to be the case. And one way to mathematically express that requirement for a general limit is using one-sided limits. What you're saying is that for a general limit to exist, the limit coming from the left and the limit coming from the right have to be the same, right? If you're sandwiching a value, then as you're approaching A from the left, the output is approaching a certain L value from below. If you're approaching A from the right, the output is approaching an L value from above. So you're sandwiching that L value. And you can see how the left-hand limit and the right-hand limit are the same, but it doesn't have to be a sandwich process. It's anything. Right here, you're not sandwiching L, but still coming from the left and coming from the right, you're approaching the same value. So the limit in general exists and is equal to L because the one-sided limits are both equal to L. Okay, so now with our understanding of one-sided limits, we can start to look at these practice exercises involving graphical limits, which are really useful for building your intuition of limits. So, okay, based on this graph here, let's state what these limits are. So what is the limit as x approaches 2 from the left of this entire function is g of x. So as x approaches 2 from the left of 2. So we're coming from the left of 2 right now. But look, the function doesn't exist here. It's an open circle. Well, it exists at 2, but it's not equal to this value. It's equal to this value over here. So what does that mean? Well, it doesn't mean anything at all when it comes to evaluating limits, right? Who cares what's happening at the actual limit value itself? So 2 itself. No, as x approaches 2 from the left, we could get as arbitrarily close to x is equal to 2 from the left, 1.999, 1.999 a trillion nines. And we're going to be, what's going to be the output we're going to be seeing is getting closer and closer to 3 from below 3. But the fact that it's below 3 doesn't matter. We're going to get closer and closer and closer and closer and closer to 2 from below 2. Below 2 because it's a left-hand limit. And we're going to see the output getting closer and closer and closer and closer and closer to 3. Okay, now what about the limit as x approaches 2 from the right of this function, well, okay, we come to the function, and now we're coming to 2 from the right. Oh, well, the function doesn't even exist here either, but so what? The function doesn't exist at 2, but who cares, right? As we plug in x is equal to 2.01, 2.001, 2.000, a trillion zeros 1, we're going to see that the output is getting closer and closer and closer to 1. Coming from above 1, but I'm just stating that just to give you some specific information. The fact that we're coming from above or below the output doesn't mean anything. We just know that this output is going to be approaching 1 as x approaches 2 from the right. Okay, now what about as x approaches 2 in general? The limit as x approaches 2 in general of g of x. So this is not a one-sided limit. Well, this doesn't exist, right? And it's based on this definition here, because the one-sided limits as x approaches 2 aren't the same. In general, what's the limit as x approaches 2 in general? Well, look, it's 2 different values. It's not approaching anything unique. Okay, what about the limit as x approaches, the one-sided limit as x approaches 5 from the left of this function? So here's 5. We're coming from the left. Okay, now this is a little bit different, right? We've got here, this is like a jump discontinuity. This is more of a removable discontinuity, like a hole. But so what? Who cares? Again, who cares what's happening at the limit value itself when it comes to evaluating limits? Means absolutely nothing. We could just see here, if we were plugging in with some huge calculator values into this function that were closer and closer and closer and closer and closer to x equal to 5, coming from below 5, so 4.999, a trillion nines, etc., we would be seeing that the output would be getting closer and closer and closer and closer to 2. Coming from below 2, but again, I'm just stating coming from below 2 for clarity. That the fact that we're coming from below 2 or above 2, that doesn't matter. Okay? Coming from the right, we're also approaching 2. So now as x approaches 5 in general, we are approaching the same value. It's not being sandwiched, but the sandwiching doesn't matter. We're approaching the exact same value coming from as x approaches 5 in general, so this limit does exist, and it's equal to 2. Okay, but they're pointing out here that, g of 5, the function evaluated at 5 is not equal to 2. So they're talking about how, so if you evaluated g at 2, g of 2 doesn't exist, right? There's no closed circle anywhere. And then g of 5 is equal to 1. But again, who cares? Who cares? This could be equal to unicorn. G of 2 could be equal to, you output a unicorn. Doesn't matter. Not when it comes to evaluating limits. That's such an important point that you need to understand about evaluating limits. That what's happening, what the function is doing at the limit value itself means absolutely nothing. We are going to see in the upcoming sections that a trick that you can use to evaluate a limit is you can plug in the actual value itself into the function and see what results, and that can help you to analyze the limit, but that's just a trick to help analyze the limit. In regards to actually analyzing the limit itself, to understanding what the limit means and the definition of the limit and how it's evaluated, what the function is doing at the limit value itself is completely meaningless. Okay, now the next specific category of a limit outside of the general category, so we just talked about one-sided limits, and next we're going to talk about what's called an infinite limit. So an infinite limit is a limit that approaches infinity. So you've got an infinite limit is you have a limit as x approaches a of a function, okay? And if you're dealing with an infinite limit, then the limit is going to approach either positive or negative infinity. Okay, now this you don't want to confuse this with what's called a limit at infinity, which we'll discuss in section 2.6. Limits at infinity are different than infinite limits in that a limit at infinity is a limit to where you're saying the limit as x approaches positive or negative infinity of a function. And this could be equal to a unique value, L. Or you could potentially have a limit at infinity that's also an infinite limit, in that this is equal to plus or minus infinity. Okay? But so we'll talk about limits at infinity later. Right now we're going to talk about infinite limits, which once again, you've got the limit as x approaches just a general number input a of a function. It's an infinite limit if the output of the limit is equal to plus or minus infinity. Okay, so find the limit as x approaches 0 of 1 over x squared if it exists. So the limit as x approaches 0 of the function 1 over x squared. All right, so we go back to the trusty calculator method. We start inputting values of x that are closer and closer to the limit value, the input value specified into the calculator. Okay, so now this is not a one-sided limit, it's a general limit, so we're going to be inputting x values above and below 0. But since this is an even function, right, with the x squared, we can just say, okay, x is equal to plus or minus 1 is going to have the same output, right? The plus and minus the same value is going to have the same output. So they start inputting values, getting closer and closer and closer to 0, from above and below 0. And what's happening is the outputs are just getting bigger and bigger and bigger and bigger. So if we had a more powerful calculator and we were putting in x equal to plus or minus 0.000, 100 zeros 1. And then x is equal to plus or minus 0.000, 1,000 zeros 1, etc. Well, instead of seeing the outputs getting closer and closer and closer and closer to some single value, we would just see that the outputs are ballooning to larger and larger and infinitely larger numbers. So the values of f of the function can be made arbitrarily large by taking x close enough to 0. Right? We can keep getting closer and closer and closer to 0 with some enormously powerful calculator. 0.000, a million zeros, a trillion zeros, a quintillion zeros 1, and we're just going to continue as long as we're not at 0, because the function we can't divide by 0, the function doesn't exist at 0. But as long as we're not at 0, we're just going to continue to get larger and larger and larger and larger numbers the closer and closer we get to 0. Okay, so it says, thus, the values of f of x do not approach a number. So we state that the limit as x approaches 0 of 1 over x squared does not exist. Okay, so again, what do they mean by this statement here? Just like we talked about with the one-sided limits, for a limit to exist, you need the limit to approach a single, distinct, unique number, right? But we just saw here that that's not the case here. Okay, however, we can indicate behavior like this. We can make a statement for the specifics of how this limit doesn't exist, the nature of how it doesn't exist. What we state is that, yes, so this limit doesn't exist, but we can, because of the unique way it doesn't exist, we make the statement that this limit is quote-unquote equal to infinity. So quote-unquote, because the limit doesn't exist, this is not really equal to anything, but this is a way that we can describe the limit. We can indicate to someone that, yes, this limit doesn't exist, but it's, in this case, this is ballooning to larger and larger positive numbers as you get closer and closer to 0. Right? So it's just a useful way of describing this limit using the infinity. Okay? But it says here that this does not mean that we are regarding infinity as a number, nor does it mean that the limit exists. It simply expresses the particular way in which the limit does not exist. 1 over x squared can be made as large as we like by taking x close enough to 0. Okay, and so it's important that we're clear on what exactly infinity means. The term infinity, this infinity symbol, which you can state as plus or minus infinity. If you're ballooning to larger and larger in magnitude negative numbers, then that's what negative infinity would mean. Okay, you might have already been exposed a little bit to the term infinity in algebra, but infinity is a very fundamental, important concept in calculus, really fundamental to calculus. So it's important that we're clear on what exactly infinity means. All right, so what did they mean here by that infinity is not a number? What does that mean? Well, okay, infinity is not a number in the sense that it doesn't make sense to make a statement like infinity is equal to infinity, or sort of an equivalent type of statement would be to say that infinity minus infinity is equal to 0. These statements don't make sense, which is confusing because it's the same symbol, right? Like we can't, like with variables, we can say that A is equal to A or B is equal to B and X minus X is equal to 0, right? Yes, that's true, but these aren't variables. Infinity is not a variable, and infinity is not a number either. Okay, so why not? Why don't these statements make sense? Okay, well, it's because infinity is just an abstract concept, an abstract statement. I could say that 100 trillion is infinity, or 500 quintillion is infinity, right? I'm not making any statement about a specific unique number when I say infinity. Infinity is relative to the context. An infinitely large number in one context might not be an infinitely large number in another context, right? If I'm talking about atoms, then a count on the order of something like times 10 to the 23rd, that's not infinitely large at all, right? That's the Avogadro's number is on the order of 10 to the 23rd. But referring to a count of baseballs on the order of 10 to the 23rd is, you could consider that is infinitely large, right? For some specific problem you're working on, a count of baseballs on the order of 10 to the 23rd, you've just ballooned to infinity, right? We could go through this same kind of analysis of a limit like this with another function other than 1 over x squared, maybe 1 over x or 1 over x cubed, 1 over x to the 4th. And as x approaches 0, you're going to get a similar result, right? As you're getting closer and closer to 0, the outputs are just ballooning to larger and larger and larger numbers, arbitrarily large numbers. Well, okay, the rate at which the functions balloon to the larger and larger numbers is going to be different, right? The actual numbers you're getting, if you did a table like this for 1 over x or 1 over x cubed, etc., the ballooning numbers are different, right? But you would still just call, in both cases, that the function is just ballooning to infinity. But again, the numbers are different in those cases. Even so, still, you're just using this symbol here, this term infinity, to make an abstract statement. It's not a unique number. The term infinity is just used to make a statement of how the magnitude of something is arbitrarily large, in like the positive or negative magnitude. That's it. Okay, but again, we still use the infinity symbol to give a description of the specific behavior of a limit when applicable. That there's certain limits that don't exist in a unique way, the unique way being that the limit doesn't exist in that the outputs are ballooning to either arbitrarily large numbers of positive magnitude or arbitrarily large numbers of negative magnitude. Okay, so we indicate this using the infinity symbol, right? So like some limits aren't going to exist if we come back here as t approaches 0 in general of the Heaviside function. This limit doesn't exist. It doesn't exist but it's not existing in some unique way that we specify with a certain symbol. This limit just doesn't exist. We state it doesn't exist. Infinite limits don't exist in a unique way that we specify using the infinity symbol. That's it. Okay, and so if we think about an intuitive, more official definition of an infinite limit, which again is a limit that approaches infinity, positive or negative infinity, then we're saying that, okay, let f be a function defined on both sides of a. So we're thinking about not a one-sided limit here, but a general limit. So for a general limit to exist, you need the function to be defined on both sides of a, but what happens at a doesn't matter. Then as the limit as x approaches a in general of the function is equal to infinity. This is an infinite limit. We're just thinking about the moment positive infinity, means that the values of f of x can be made arbitrarily large as we please, by taking x sufficiently close to a, but not equal to a. Okay, and so if we break this intuitive definition down from the perspective of our trusty, hypothetical, enormously powerful calculator, what they're saying is this. Okay, so we need to be able to do this as we approach a from both sides. So since this is not a one-sided limit, we have to be able to make a table. One table with x approaching a from below, and another table with x approaching a from above. Okay, and in both cases, the idea is, so we can plug in values of x to trillions of decimal places, quintillions of decimal places that are just below a and just above a. And as we get closer and closer and closer to a, the function output is just getting larger and larger and larger in positive magnitude for both cases here. This needs to be the case happening on both sides. And the way that they express this is that, so like, what does larger and larger in magnitude mean? What exactly does that mean? How large is large in magnitude, right? What they're saying is that someone could give us a number, some huge number, no matter how huge it is. And because we have this infinitely powerful calculator, then we can say, okay, then I could produce that number for you, whatever huge number you specify. I could produce that number for you or something close to it by just making x close enough to a on either side of a. That's it. That's the idea. There's no number that's too big that we can't, with our huge calculator, that we can't get an output that's close to that number by just plugging in a value of x as the input from either side of a that's close enough to a. That's the intuitive meaning of an infinite limit, right? So if we look here, that's exactly what's happening with the function 1 over x squared as x approaches 0 from either side, right? You're getting this ballooning to positive infinity process on both sides, right? You can think about how this needs to be happening on both sides to state positive infinity like this. Similar to how general limits work with respect to when the limit exists and you're approaching L from both sides. So like if, for example, we'll see in a second, if on one side you're ballooning to large positive values, but on the other side of the limit value, you're ballooning to large negative values. So the limit is it's an infinite limit. It's ballooning to large numbers in magnitude coming from both sides. But since you're ballooning to positive values on one side and negative values on the other side, then you just have to say that the limit doesn't exist, D and E. Because you can't put the positive infinity value or the negative infinity value, right? Okay. Another notation for the limit as x approaches a of f of x is equal to infinity is, so just an arrow like this. You can use an arrow like this to make the statement of approaches. F of x approaches infinity as x approaches a. All right, and here's another graphical illustration of an infinite limit as of a function as x approaches a in general from both sides. You're ballooning to large positive numbers in magnitude on both sides. Okay, but then Now we're going to think about an infinite limit in regards to negative infinity, right? Here you're ballooning to larger and larger values of magnitude that are negative. So it's the same idea. Let f be a function defined on both sides of a, except possibly at a itself. We don't care what's happening at a itself. Then the limit as x approaches to a of f of x is equal to negative infinity means that the values of f of x can be made arbitrarily large negative numbers by taking x sufficiently close to a but not equal to a. Yeah, it's the exact same idea, just in regards to large negative numbers in magnitude. So if we took this function here, this 1 over x squared, and just multiplied it by minus 1, we would flip this about the x-axis, right? And so if we thought about the limit as x approaches 0 in general of the function minus 1 over x squared, well, that's what they show here. That's going to be negative infinity. Okay? But now for the case that I mentioned of how the limit as x approaches 0 of a function like this also doesn't exist, but you can't specify that the limit is equal to positive or negative infinity because you're not approaching positive infinity on both sides or negative infinity on both sides, right? So you would just have to say that this function, if this is g of x, this is 0, you have to say the limit as x approaches 0 in general of g of x, you would just have to say d and e. Okay, but we can specify limits here as infinite limits from the perspective of one-sided limits. We could say that the limit as x approaches 0 from the left of g of x is equal to negative infinity, or the limit as x approaches 0 from the right of g of x is equal to positive infinity, right? And that's what they're talking about here. It's you have one-sided infinite limits. So here's 4 cases of one-sided infinite limits. You can't state that the limit as x approaches a in general of this function is equal to infinity because there's nothing happening on the right side. But you can make a one-sided infinite limit here, right? So, okay, the vertical line x is equal to a is called a vertical asymptote of the curve y is equal to f of x if at least one of the following statements is true. So we talked about vertical asymptotes in algebra. We touched on vertical asymptotes a little bit in algebra, but now in calculus, we're going to get a more official definition of what exactly a vertical asymptote is. Okay, and what a vertical asymptote is it's any vertical line which you represent a vertical line mathematically as x is equal to a number, right? This is a vertical line. X is equal to some finite number. Okay, well, if the limit as x approaches a of some function, okay, is equal to positive or negative infinity, but the x approaching a could be from any perspective. This could be x approaching a in general. This could be a one-sided limit, whatever. If just one limit as x approaches a of a function from any perspective. So here they give the perspectives of the x approaching a in general, x approaching a from the left, x approaching a from the right. And in any case, if a positive or negative infinity is the output, doesn't matter, right? Here, so x approaching a in general from the left, from the right. Same here, but this is all positive infinity, all negative infinity. If any one of these statements are true for a vertical line x is equal to a with respect to a function, then that's a vertical asymptote, is what they're saying. These are all vertical asymptotes. This is a vertical asymptote. This is a vertical asymptote. This is a vertical asymptote. So, okay. Find the limit as x approaches 3 from the right of the function 2x over x minus 3 as well as the limit as x approaches 3 from the left of that same function. So, okay, how can we analyze this? Well, all right, if x is close to 3 but larger than 3, then we know that x minus 3 is always going to be positive, right? And if x is close to 3, positive 3, but always larger than 3, then 2 times x is always going to be positive, right? But we know when it comes to dividing by 0, if we're letting x get closer and closer and closer to 3, coming from above or below 3, we're going to be getting a smaller and smaller and smaller number in the denominator, closer and closer and closer to 0. We can't divide by 0, but as long as we're not at 0, this function exists, right? And we know when you're dividing by a smaller and smaller and smaller number, as long as what's happening in the numerator isn't also like approaching 0 or something, which this isn't. As we would get closer and closer and closer to 3 here, this would be approaching like 6 from above or below 6. Well, if we're coming from above 3, this would be approaching 6 from above 6. But we're going to be dividing by a number that's closer and closer and closer and closer to 0 in the denominator. In particular, it's going to be a smaller and smaller and smaller positive number because we're always going to be, x is always going to be above 3. So you can see from that analysis, this is going to be ballooning as x approaches 3 from above. This is going to be ballooning to positive infinity, right? And with a similar analysis here, as x approaches 3 from below, the numerator is still going to always be positive because it's still just positive 3. You're just 2 times x as x approaches 3 from below is going to be approaching 6 from below 6, but still positive 6. But x minus 3 is going to be getting closer and closer and closer to 0, but coming from below 0. This is going to be a smaller and smaller and smaller negative number. So, but like a positive number divided by a smaller and smaller and smaller negative number this is going to balloon to negative infinity, right? And that's what the graph of 2x over x minus 3 indicates. You can't divide by 0. So the function doesn't exist at x is equal to 3, which doesn't matter. But coming from the right, we're ballooning to infinity. Coming from the left, we're ballooning to negative infinity. And so that's what the two one-sided limits are equal to. And you've got this vertical asymptote at x is equal to 3. But in general, though, we would say that the limit as x approaches 3 in general we would say that this does not exist. We can't use the infinity symbols here. Okay, now this last example says find the vertical asymptotes of f of x is equal to tangent of x. So, okay, tangent of x we can write as sine of x over cosine of x. And it says, so when it comes to vertical asymptotes, we want to think about the scenarios that are related to dividing by 0, right? When you're dividing by tiny numbers, that's when you're ballooning to large numbers in magnitude. So there are potential vertical asymptotes where cosine of x is equal to 0, right? In fact, since cosine of x approaches 0 from the right side of 0 as x approaches positive pi over 2 from the left side of pi over 2. So what they're saying is that if we think about cosine, so you've got a period is 2 pi, half a period is pi, so like this is pi over 2. So as x approaches pi over 2 from the left, cosine of x is approaching 0 from above 0, right? You see, that's what they're saying. And as x is approaching pi over 2 from the right side of pi over 2, cosine of x is approaching 0 from below 0, whereas sine of x is positive. It's near 1 when x is near pi over 2. So sine of x would be right, like this is 2 pi, there's pi over 2 for sine of x. Then what they're trying to say is that as if we think about as x approaches, for tangent of x, as x approaches pi over 2 from either side, we're just going to have some finite number right around 1 coming from either side in the numerator. But in the denominator, we're going to be having also a finite number, but it's going to be very tiny, close to 0. Whereas in the denominator with cosine of x, it's also a finite number, but it's very tiny, very close to 0. Yeah, depending on the direction, it could be a very tiny positive or negative number, but still close to 0. And so like a number right around 1 divided by a tiny positive or negative number is going to be some infinitely large number, right? Because you can get as arbitrarily close to pi over 2 as you want with a huge calculator, right? So we can just make this balloon as much as we want, as large as we want in the positive or negative direction. And so we can state that what this shows us is that as x approaches pi over 2 from the left, so the sine of x is approaching 1 from below 1, coming from the left or the right. But in the denominator, we're approaching as x approaches pi over 2 from the left, we have a smaller and smaller and smaller and smaller positive number. So this limit, one-side limit, is equal to infinity. And then as x approaches pi over 2 from the right, still just approaching 1 from below, but the denominator is approaching, getting closer and closer and closer and closer to 0, but from below. So it's negative. So this one-side limit is negative infinity, right? And so like there's the vertical asymptote at pi over 2. But this is a tangent is periodic with period pi, so each vertical asymptote is going to be at like we can start at pi over 2 and just go plus or minus in pi, and you're going to get to another vertical asymptote. But we can see that in general, we can't say that the limit as for tangent, we can't, if we said the limit as x approaches pi over 2 in general, or like any integer times pi over 2, or integer times, what would it be? You go pi over 2, then minus pi, or plus pi. We can't say that in general, not one-sided, this limit of tangent of x is equal to like plus or minus infinity. No, this would be does not exist. Okay. Another example of a function whose graph has a vertical asymptote is the natural logarithmic function. So yeah, we can see that you could state that the limit as x approaches 0 from the right, but not in general, because the function doesn't even exist over here, of natural log of x is negative infinity. And you could also state, we haven't gotten to limits at infinity yet, but you could also state that the limit as x approaches infinity of natural log of x is equal to infinity. And this is a good illustration of that. So with the natural log, this isn't increasing very fast, right? As opposed to something like x cubed balloons fast. But this is a good illustration of how that doesn't matter. Infinity is an abstract concept. This is still just ballooning. You could make x as, with an infinitely powerful calculator, you could make x as arbitrarily large as you want and get as large of an output value as you want with natural log of x, right?